Okay, hello everyone, let's get started. So, welcome to another lecture as part of our ID 5130, the Parallel Scientific Computing course. Okay, so in the last lecture, we kind of looked at some of the variable data access clauses, right, or data scope attribute classes, right. Essentially, we looked at some of them. Some of the examples are, we looked at private, right. The other one is shared data clause. Similarly, we also looked at something known as default, right, where default can be either none, or it could be private, or it could be shared, and also we looked at something known as last private, right. Sorry, we looked at something known as first private, right. So where as soon as the private variable enters a parallel block, the values for each of the thread copies will be excuse me, will be copied from the original value that is available on the master thread. Excuse me. So today we will continue our discussion with this. We will also look at few more variable data scope attribute classes. So the first one is, the next one is basically the last private, and a list. Okay. So similar to first private, last private can be easily guessed what it does. So what it does is basically, if you have a parallel block, any of the private variables, as soon as they exit from the parallel block, will have undefined values, right? Will have unspecified values. Okay. So as a result, if you would like to copy the last value into the original variable upon exit from the parallel block, then we are going to use this particular clause that is known as last private. Okay, now I just said something. I said last. Now what is last? Is it actually the value obtained by a thread that happens to be last? No, it is not that. It is basically the last value that would be obtained. Okay, the final last value that would be obtained if the loop, if the loop were to be run in serial. That means it is the last value in the loop, in the iterations as such. Okay, so that means, let me kind of give an example here. Let's say in C we would write this as hash pragma OMP. Let's say we have a parallel for, okay, and then we have we declare private as one variable. Let's say private is I, that is the loop variable, and then I would also say another variable that I will be using as last private A. Okay, so A is a last private variable, and then because this is hash pragma parallel OpenMP parallel for, this needs to be immediately followed by a for loop for I equals 0, I less than, let's say less than or equal to, or less than 1000. Okay, let me make it I equal to 1. That's kind of easy. Okay, I plus plus. Okay, and then we say A equals to I. Okay, so basically we have the twice of the iteration is copied to A. Now A is also declared as last private. That means it is also a not only a private variable, but it also has the special attribute that it is a last private variable. Okay, that means that once the loop is over, whatever is the last value that would be obtained if it were run in serial, that means the value of 1000, okay, will be the last value that will be copied to A. Okay, so that means upon exit, A will have a value of 2000 upon exit from this particular block of the parallel block. Okay, so that is what last private means. So this is somewhat sometimes it is convenient to have variables to be updated with the last values. Okay, that is when you can use this. Now, what will be the similar Fortran code? So Fortran code would be exclamation $OMP. You would have a parallel block and then parallel do. Okay, I would say the rest of the things are very similar. Private I and then last private A. Okay, that's what we have. And then of course you have a do loop, do I equals 1 to 1000 in the increments of 1. That is optional. The 1 is optional. And then you have, let's say, A equals 2 times I. And then you have and do. Okay, and then you would also need exclamation $. Unlike C, you would need this extra AND directive pair that is called AND parallel do. Okay, so that's what you have. That's how you write it in Fortran. Okay, all right. So now that is kind of what last private does. Let us look at another clause. So what is the numbering? Did I say 1? Okay, let me just put it as 1 here. Okay, so the next one is actually comes as a pair. So I would talk about something known as Threadprivate. So Threadprivate and then a list of variables. Okay, and then followed by copy in followed by list of variables. Okay, so I'm kind of discussing two of them because these two kind of go kind of hand in hand. So what Threadprivate is? Threadprivate is actually not a clause for the parallel directive. Okay, it's not a clause for the parallel or parallel for. Okay, I meant to say it is not a class of parallel or parallel for. I mean to say that we would not declare it at together with this. Okay, rather we should declare this much ahead. Okay, that means we should use Threadprivate at or immediately following the variable declarations. Well, that is in kind of Fortran, but I think in C it is probably allowed even if you do it later. Okay, just like the other functionality that C has. Okay, so that's what it is. Then let us see what is Threadprivate. So let us say you have, I mean, as the name suggests, you basically are defining a list of variables that is private to a thread. Okay, but then let us say you want to calculate derivative of a function. So let's say our function is f of x, and you would like to calculate what is df dx. Okay, is what you need to calculate. Now let us say if df dx needs to be calculated in parallel by several threads. Okay, now that means df dx is an array. So if you have f as an array of n values, and then you would say df dx is also an array of n values. Now this n will be calculated by each of the threads. So each thread will get to work with n by p, where p is the total number of threads you have, right? Okay, so that means and then you also would like to do like you will be using, sorry, this should be df dx. So and then while the program that you would write would need df dx values at let's say several instances, and then in each of the instances you would be using, let's say, a different formula to calculate df dx, or rather it may be possible that your f of x has changed in between as well. So you may, even if you use the same formula, your f of x has changed. As a result, you need to recompute what is df dx. And then now let us say n is a large number. Okay, so the idea here is that you don't want to so essentially you don't want to keep allocating df dx okay, and deallocate this each time you call a parallel block, okay. And you also would like to keep this df/dx, okay, whatever is the previously computed values when you fork again. So when in the next forking, you would like to keep these values that are calculated before. So that means there is only a way you can get this is basically you can have, if you have somehow df/dx for each of the threads, the local copies needs to be preserved, okay, instead of being destroyed. So if you would like to do that, that not only saves the overhead of creating the df/dx each time a parallel block forks into several threads. So what you can do is you can declare this a particular variable as a thread private. Okay, how do you declare this? Basically again using the hash pragma. So you would say a hash pragma OMP, you would say thread private, okay, thread private, and then you would give list of variables. That means you would give, let's say, df/dx here, okay, so df/dx, and whatever is the array that you would like to have. So it's going to create so many copies, okay, for each thread. Okay, that means it is going to replicate the variable memory so that it persists throughout the program, okay, so that it persists throughout the program. Now of course with such a implementation, you are not allowed to have dynamically varying number of threads. So that means if you have started your program with, let's say, 10 threads, you should continue to use only 10 threads throughout the program, okay. Otherwise, of course, you the problem you run into is that you don't have allocation for the 11th thread if you change the number of threads. As a result, this implementation will only work if you have set your dynamic threading to false, okay. That means you have to before you go into the parallel sections or parallel regions, you need to set this variable OMP set dynamic. You need to kind of use this runtime library and then call this function set dynamic equal to 0. That means it's going to set the dynamic threading to false, okay. So that means dynamic threading is not allowed, so you'll only work with whatever is the number of threads that were set before. So in Fortran, you would write it as exclamation dollar OMP thread private, and then you would give the list of variables. Now and then you would also make a call to OMP set dynamic to with an argument logical operation FLASE false with dot preceded and at the end, okay. Alright, so basically this will now define. Now I have a question for you. Now what will be the length of df/dx that you should set? df/dx, should you set, let's say if you have n values, should you set n by p as here, or should you set n, okay. So you need to check that. Should it be like this or should it be like this, so that every thread will get a copy of df/dx. Now as I said, thread private will basically will allocate a local and persistent to a thread that is that exists throughout the execution of the multiple parallel threads, okay. So in order to see this thing, let us take an example, okay. So and see. So now hopefully you would understand the difference between, let's say, thread private and a private, right? In a private, the variables, the memory is created and deleted and created and deleted in each time you call different parallel regions. Whereas in thread private, once the memory is created, that will persist throughout the entire program, and not only that, the data that it has, the variables have, will also persist between the different parallel regions, okay. That is the difference. All right. So now similar to private variables, on a first entry to a parallel region, the thread private variables will have undefined values. Okay, so that is the same. All right, let us see an implementation. So if you are in if you are using C, then you would have, let's say if you have int, you declare int a, and then let's say you have a floating point variable x, then you would declare hash pragma OMP. I would declare thread private as let's say I would declare a comma x as the thread private variables, okay, or something like that. I can just declare, you know, maybe just a, that is fine. Okay, then if you are in Fortran, then how do you declare? You would basically say integer, let's say if you have integer I, or if you have real value of x or something, then you would declare basically exclamation dollar OMP thread private values of x comma I, okay, something like this. All right, now let us see an example. Okay, once you have declared using a thread private variable, let's say we have declared a as the thread private variable. Okay, so this is now declared, so a is a thread private variable that we have declared in the program, and within the program we have, let's say, 3 parallel regions. Okay, so the first one is basically okay, so basically we have exclamation dollar. I would use Fortran here, OMP. I have declared thread private a, okay, so that is now declared in the declaration section. And then once you come down, you have parallel region, so you have OMP parallel, okay, and then inside the OMP parallel you have let's say you set a value of a, okay, let's say a is now set to the thread number. Okay, let's say this is your OMP get thread num, I don't need the semicolon, okay, and then I would say exclamation dollar OMP and parallel, okay, and then I have another parallel region after this, exclamation dollar OMP parallel, and then I do something here. Okay, we do something here, and then in between you have basically some serial code, and then exclamation dollar I have OMP and parallel, okay. Then I have again some serial code followed by exclamation dollar OMP parallel, okay, and what I do is again we have some data, and then I would use OMP parallel, and this is where I say the other clause that we learned, okay, copy in the values of a. Okay, now copy in can only be used together with thread private variables only. Okay, okay, so in the end clause of this thing, oh sorry, this should be end parallel, right, OMP end parallel copy in. Okay, so I would use this, and then again we have, let's say, some serial code, and then followed by exclamation dollar OMP and parallel. Okay, fine, so that's basically I have OMP parallel, OMP and parallel. Yeah, so that is fine. Okay, then I don't need this end parallel again, so I don't need this one. Okay, so this is some serial code. Fine, so what we have is basically we have now 3 regions, right, 3 parallel regions. This is one, and then we have a serial, then we have sorry, first one is, where is the first one? So this is the first one, so this is the first one, this is the second one, and this is the third one, right? So in the first one what we are doing is we are setting a to be equal to get thread num. So basically depending on the number of threads, a is going to get either, you know, 0, 1, 2, 3 values like that. Now once it comes into the serial region, you have only a value, which would be, because a is thread private, a will still have value of 0. Okay, but then once you come out into the next parallel region, a again here a's will have 0, 1, 2, 3. So let me draw kind of a diagram here. So in the first parallel region we are setting a to be equal to the thread number. In the second parallel region we are not doing anything with it, and after exit from the third parallel region we are setting copy in the values of a. Okay, so what does this do? So basically copy in, what it does is it's going to copy in, what it does, it's going to copy the value of available of for A on the master thread to all other threads. Okay, so let us see. That means okay, so that means, let's say you have in the serial code you have thread 0. Okay, A is kind of not given a value, and then you have access to some shared memory. Okay, now once you encounter the first parallel region, so in the first parallel region, what you have is you have several threads that are created. You have T0, T1. So in T0 will have A equal to 0. T1 will set A equals 1 because you're calling this function. What is it? It's basically your OMP get thread num. Okay, so and then all the way Tn will have A equals n or n minus 1. Okay, or Tn minus 1. Yeah, Tn will have An. Fine. So and then you also have some shared memory, which is of not relevance right now. Fine. And then again you would have some serial region, and in the serial region, because you only have thread 0, A value will be equal to 0. Okay, because now this is basically a thread private variable. Then you encounter the second parallel region. In the second parallel region, if you want to access, your T0 will have A0, T1 will have A1, all of a sudden, and all the way Tn will have value of An. Okay, and then of course there is some shared memory. So these values is what I call as a persistent and preserved, right, between the parallel calls. So they are preserved, and so essentially you can create a kind of a global scope for the variables that you have for the private variables. And then you have another serial section. In the serial section you only have thread 0, which will already have A value equal to 0. Then you encounter the third parallel region, right? And in the third parallel region, what you are doing is you are basically saying, oh sorry, I think the copy in should come at the beginning of the parallel. Okay, so essentially here I would say copy in, not afterwards. Okay, that means it's going to copy in the value of the master into the values here. Okay, so in the third parallel region, what I have is I have T0, but then I have used copy in, so A equal to 0 is already there. Okay, because of the copy in function, even thread 1 is going to get the A is equal to 0 because it's going to copy this value here, and thread 2 will also get A equals 0 all the way, right? Even Tn will have A equals 0. Okay, so that's what copy in function does. Okay, with the thread private. Now, fine. All right, so that is what it is. That means it's only going to copy the value that is available on the master thread to all other threads. Fine. Okay, now let us look at one more example, one final example in the variable data scope attribute clauses. So the last one is basically known as a copy private and a list of variables. Okay, now copy private is only used with another directive called the single directive. Okay, now a single directive is something which is basically where inside a parallel region, if you put a hash pragma OMP single, then only one thread will be allowed to execute it. Okay, only one thread, and which thread will be allowed to execute it? Whichever thread arrives first to that statement will only be allowed to execute it. All other threads will not execute it, they will all skip it. Okay, only one thread will be executed. So and then whatever this particular thread executes, those values, whatever it has read or updated, those values can be broadcasted to all other threads. Okay, that means there is an implied synchronization or waiting point that is there with the single directive. Okay, so there is an implied synchronization, right, exists or is there implied synchronization in the single directive. Fine. Okay. All right, so how do you write this thing? So essentially, so many a times we don't want all the threads to, let's say, execute some statement, such as if you want to read some data from a file, or if you want to, read some data from another variable or things like that. So you don't want all of the threads to kind of compete and read it. So what you can do is in Fortran, you have exclamation dollar, you would say OMP single, okay, and then you have exclamation dollar OMP and single. Now of course when I write this is assumed that this is already in a parallel block. That means exclamation dollar OMP parallel, that means the threads are already forked, right? So within that we would use this thing exclamation dollar OMP and parallel. Okay, now the parallel and the single need not be one after the other. Okay, the parallel might have started much ahead and the single has come somewhere in between. Okay, so that is how you do in Fortran. In essentially C, what you would do is you just write hash pragma OMP single. Okay, that's what you would do. Now when it comes to let's say after this particular thread, whatever thread arrives first here would execute whatever is there in this block. Okay, so only one thread executes it, all other threads will not execute, they will be waiting here. Okay, let's say this particular thread is reading something from a file. Let's say you are reading from a file. I would write it as read 1 comma star. So this is kind of convention in Fortran. So it is reading from a file with index 1, let's say this, and then it's reading a variable a. Okay, then you want all threads to have the same value of a that is read by this particular thread to be updated. Then what you say is in the OpenMP and OMP and single, here you would write copy private a. Okay, so what it's going to do is going to copy the private value of a that is read by this particular single thread to all other threads. Now this thread could be, let's say, T5. Now let's say you have 10 threads, out of which T5 does this thing. That means T5 will now broadcast this a value and it will update this value to all other threads, that is T0 to T4 and then T6 to T9. Okay, and then because in Fortran you have this AND statement, right, because it's basically a directive pair. In C you don't have an AND kind of statement, so what you do need to do is you need to specify in the opening statement itself. Here itself you will say copy private a. Okay, that means once it finishes with the single, it's going to copy that value to all of that. That means there is an implied synchronization that is there in the copy private class, in the single class. All right, so that is kind of and again when you write this thing even in C, you assume that you basically opened a parallel region, hash pragma OMP parallel, and then you have, let's say, some clauses such as shared or whatever. So that is there, and then inside this somewhere you end up with hash pragma OMP single with, if you wish, you can have a copy private clause, otherwise it's not required. Okay, so copy private whatever is the list of variables. Okay, that is how it will be in C. Fine, so we are already in the parallel block. Okay, so the threads are already there, and then out of that whichever thread arrives here first will be executing this code that is kind of there in the OMP single. Okay, all right, so far so good. Then we also have so that those are about the variable data scope attribute clauses. Let us also look at a few miscellaneous clauses, and then we will look at some more work sharing clauses as well that we have missed in the previous lectures. So let us look at some miscellaneous clauses. So OpenMP allows for several clauses, and some of the miscellaneous ones are if clause. Okay, so if, and you have some kind of a scalar logical expression. Okay, so that means it should turn out to be either 0, 1 or true or false. So if is, as you know, is basically a conditional clause, and then OpenMP gives you an if as well. Now what do you do with this if that OpenMP gives you, and why is it required? So well, it is basically required. Let's say you have several for loops or do loops. Okay, and you realize that you don't have to kind of run them in parallel all the time. Okay, because let's say for example you have a n that kind of defines how many iterations are there in a for loop or a do loop, and then if this n is, let's say, only if this n is greater than, let's say, 1000 or something like that, you would like to create, you would like to fork threads and then run them in parallel. Okay, and you realize that there is some overhead associated with the creation of the forks and kind of joining them and creating the private variables and things like that. So as a result, if a particular for loop that you have has less than 1000 values, okay, then you better off maybe running the code in serial, because that may run faster than the parallel code. Okay, so what you can do is, while coding it itself, what you can do is you can say, let's say if I have hash pragma OMP parallel for, okay, and you can say only if the n is greater than 1000 or something like that, you run the for I equals 0, I less than 1000, I plus plus. Okay, only then you run this in parallel, otherwise just continue in serial. Okay, so that is what this condition if n greater than 1000 tells you. Okay, so you can use that, which will probably be sometimes faster. Okay, and such conditions will be very will be very much used in commercial codes or open source codes if you look into some of their programs. All right, so now how do you do this in Fortran? So essentially you have exclamation dollar OMP parallel. Okay, only if n is greater than 1000 you would execute this thing. So this is exclamation dollar OMP do. Okay, because parallel is already in the section, so I just need a do loop here, and then I would say do I equals 1 to n in steps of 1, and then you have some loop here, and you have end do exclamation dollar OMP end do, that is closing for this one, and then exclamation dollar OMP end parallel. Okay, so that is your corresponding Fortran code. All right, then so it will be only executed if the number is greater than 1000, otherwise it will be executed in a serial fashion. All right, so in addition to another miscellaneous class that we have is known as a NoWait class. Okay, as the name suggests, it tells that for the threads to not wait. That means we are basically not synchronizing them. A thread is free to move ahead even if the other threads have not finished. So this is basically is kind of sometimes we feel that, let's say if we have two blocks, okay, which are executed by different threads, let's say T0 executes this one, and then or T1 has done this one, and there is no dependency between the block 1 and the block 2. Okay, no dependency. Then T1 after finishing this part can go ahead with executing whatever its part in the second part, right, in the second block. So that is where you can use this kind of NoWait class, but NoWait needs to be used with care, because it will also suppress the implied data synchronizations as well. Okay, so for example, let me write again in, let's say in Fortran or something, exclamation dollar, I have OMP parallel. Okay, and then we have a do loop, exclamation dollar OMP do, and then we have do I equals 1 to 1000 comma 1. Okay, so essentially I have, let's say, a of I am updating a of I using I plus 2 or something. Okay, so I plus 2, we have end do. Okay, and then you say exclamation dollar OMP end do NoWait. Okay, and do NoWait. That means when this thread is being executed in parallel, once, let's say, T0, T1 or T2, any of them, if they finish, they don't have to wait for a synchronization here. They can move and do the next statement, whatever is the statement that they find. So that is, let's say you have another do loop, exclamation dollar OMP do. Okay, we have another do loop, do I equals 1 to 2000 comma in steps of 1, and then you have some b of I equals let's say I star 5 plus 2 star, or maybe just 2, okay, or some 10, fine. and then we have and do, okay, exclamation dollar OMP and do, and then you have exclamation dollar OMP and parallel. Okay, so well, here what you can see is that you can see that these two are, you know, the second one does not depend on the first do loop, right? So as a result, T0 or T1 or any of those threads can continue to go to the next one without waiting for all of them to be there. So it means we have kind of suppressed the data, the synchronization that we have between the threads. Okay. Now, how would you write this in C? I mean, essentially, when you write, you would put the NoWait clause in the parallel for itself. Essentially, you write hash pragma. Let's say we already have a parallel open, then we say OMP for, you say NoWait, right? Okay, and then you already have a hash pragma parallel in which the threads are already forked here. Okay, okay. So you would attach the NoWait in the opening statement itself, because there is no closing directive pair in C, whereas in Fortran you would attach it to the closing directive pair. Okay, all right. Okay, so we have already seen in the miscellaneous clauses. Now in the context of synchronization, there is another synchronization that we can discuss, that is basically similar to the single directive. We also have something known as a master directive. Okay, so within a parallel block, you can allow, or you can kind of direct only the master thread to execute a particular structured block, and all other threads need not execute that. Okay, so this is more like a single thread, whereas here the single thread is forced to be the master. Okay, so what you can do is essentially, if you have a parallel block, let's say I have hash pragma OMP parallel. Okay, so within that I can say hash pragma OMP master. Okay, that means only the master thread will execute this following statement. Okay, following structured block. Okay, this is only executed by the master, that is only by T0, and all other threads will not wait. Okay, so there is no synchronization. This is unlike the single thread. In the single thread, all of them will wait. In the master class, only the master will do, and all other threads can move on. Okay, so T1 will move on, T2 will move on, and so on. Okay, so if I were to write in Fortran, I have exclamation dollar OMP parallel. So we are already in the parallel region, and then what we have is we have exclamation dollar OMP master, and then you have a block of code, structured block, exclamation OMP and master. Okay, and then we also will end the parallel block. Okay, so if I were to kind of draw this one, so let us say if you have OMP master here, let's say it's kind of printing hello. Okay, so let's say you have write to the screen, you print hello. Okay, then what will happen is that T0, which is the master thread, when it encounters this thing, it's going to print hello, and it's going to come, whereas T1 thread, when it comes here, it's going to not do anything, it's just going to race ahead without the master and all other threads, right? So as a result, once the master thread finishes, it is now lagging behind the other threads. Okay, so the master directive is like, you know, if you were to draw parallel, is like the single directive that we have seen earlier, right, with the NoWait clause. So you add a NoWait clause to a single directive, and also of course you force T0 to execute it. You know, that is where the master comes into play. Okay, so that is the difference between a single directive with a NoWait clause and a master directive. In a single directive, it will basically, all of them will wait for synchronization, and if you add NoWait, they will not wait. But then the single will not guarantee that it will be executed by master. It will be executed by any thread that arrives first, whereas in master only the T0 will execute it. Okay, fine. So we have also seen a few other synchronization directives. The other one is, okay, this is number 4, not 2. Okay, the other one is critical, right? We have also seen a critical where it will be executed by one thread at a time, right? So that is a critical directive that we have already seen in the lectures before. In a critical directive, is there synchronization at the exit? Yes, there is a synchronization at the exit of from the loop. So all of them from the block. So all the threads will wait, because each of them will do it one after the other. There is a mutually exclusive access to execute the structured block of code. Okay. In addition, we have another synchronization directive is known as the barrier directive. Okay. So what does a barrier directive do? It's basically will represent an explicit synchronization. Let's say in some cases you would like to have an explicit synchronization, then you would basically use the barrier directive. But barrier directive in most of the cases need not be used, because we have seen that most of the calls of the directives we have some kind of a synchronization point, right? They all have a wait. Okay, but if you would like to have somewhere, then you can have this barrier directive. So the way you write it is basically you would just say in C you would just say hash pragma OMP barrier. Okay, and in Fortran you would basically say exclamation dollar OMP barrier. Of course, you have to do this inside a parallel block. Inside a parallel region. Now, but barrier directive cannot be used in whatever way you want. Okay, so barrier directive for it to be applied, there are two restrictions. The first restriction is that the barrier directive should be encountered by all the threads. Okay, that means all threads should encounter the barrier, that is all threads in the team. Okay, otherwise or by none of them at all. Okay, but in between anything else is not allowed. Okay, that means so we need to be very careful when you use the OpenMP barrier class, because there are several situations in which this may not be satisfied. We may end up with a code in which the barrier is not seen by some of the threads. Okay, if we write such a code, then essentially the program will reach a no exit point, which is not good. Okay, that means there will be a deadlock and the program will not progress. Okay, that means, let us say for example situations in which the barrier directive is not encountered by all the threads. Let's say if I have exclamation dollar, let's say OMP critical. Okay, I have critical exclamation dollar OMP and critical, and inside the critical directive I would put exclamation dollar OMP barrier. Now what will happen? Will this be okay? Well, this will not be okay, because barrier is not encountered by all the threads in the team, because only one after the other they will encounter. As a result, this will lead to a deadlock. Similarly, if you put, let's say instead of critical, if you have a single directive OMP single, or if you have a master, any of these things, if you put a barrier inside, that is a disaster. Okay, so don't do this one. Okay, because barrier is not encountered by all the threads. As a result, you end up with a deadlock of the program, and it's not good. Okay, there will be several such instances. Then this may happen even if you have, let's say, some conditional code. Let's say if the number of threads, let's say if you say my rank, if it is less than only, or if it is greater than 10, okay, you may say okay then, or only in that situations you can say hash pragma OMP barrier. Now that is not good because only if your rank is greater than them, that means all other threads T0 all the way to T9 would not see this OpenMP barrier. As a result, this will still lead to a deadlock. Okay, so such codes are need to be checked for problems like this. Now what I have given is very few examples, but if you see some, you can even encounter some complex examples, complicated codes or complex examples in which it may be difficult to find whether the barrier is used correctly or not. So as a result, it is better to not use it all the time. Hold on, just take this call, sorry for that. Okay, so essentially you can probably find very complex examples in which the barrier is used, and it may be kind of difficult to see if there is any issue with that. Okay, that means what I mean to say, whether all the threads are being given a barrier signal or not. Okay, so such things needs to be avoided. The other restriction is that the all the threads must reach barrier in the same order. Okay, that means if some of the threads execute a parallel section followed by a barrier, and if the others do not, then there will be an issue. Okay, so as a result, all the threads should reach in the same order. So all the threads should reach the barrier in the same order. It should not be different. That means you cannot have like a if-else, kind of if-else statement, and then you have barrier here and something else here and so on. Okay, so such things will lead to deadlocks. As a result, this needs to be used with care. All right. Okay, then we have a few more directives in the miscellaneous ones and in the synchronization ones. The other ones is basically known as an atomic directive. So where are we in terms of counting? Critical barrier. Okay, 6. So the 6th one is known as the atomic directive. Okay, an atomic directive is again like similar to critical. Okay, essentially atomic directive will allow only one thread to execute a statement at a time. Okay, that means all the threads will again have a mutually exclusive access. So that means they will do a statement or the structured block. Okay, so now we say it is similar to critical, but then why do we need it again? So let us see what the atomic directive does differently. So atomic directive only will provide mutually exclusive access to only one statement, only one line that precedes that is just below the directive. Okay, that means if you have basically, let's say atomic directive, let us take an example. So let's say I have a hash pragma OMP parallel. Okay, and I have hash pragma OMP for. Okay, and then we have some for loop here for I equals let's say 0, I less than n, I plus plus, and then inside this let us say we have some sum equals sum plus I. Okay, and then basically this is the end of the for loop. So in such situations, we know that the sum cannot be updated by all threads because sum is kind of shared variable, right? And it should be updated by threads in a mutually exclusive way, right? They should not be updated by all the time. So one way to look at this is you can put a critical statement around the update here, or you can even say it as a reduction operator as we saw before. Another way to do it is basically to say this as an atomic thing. Okay, so you can say hash pragma OMP atomic. So you can just add this particular line here, and then it will execute the following statement in a mutually exclusive way. Okay, this will be one thread at a time. Okay, all right, so that is what it is. Now there are, of course, so that means the atomic statement or the atomic directive is more like a kind of a miniature critical section. Okay, but then it still is not clear why do we need two of them. The only reason we need two of them is that atomic structure, atomic directive basically can be is more, or is more optimized way, because it has restrictions on what this particular line can be. Okay, essentially you cannot write whatever you want in the below the atomic statement. The particular statement that follows the atomic should be only in this particular order. It should be x equals x, some operation and some expression. Okay, so this is one way. The other way to have this is basically you have x equals some intrinsic function, okay, that takes x as well as some expression and then updates x. Okay, only these two kind of statements are allowed within the atomic below the atomic statement directive. Okay, and then there are of course limitations on what the operation should be. Operation is only allowed to be, let's say, plus, minus, multiplication, division, and then few other logical operators. And then now here comes the most difficult part. Essentially the expression should not contain x. Okay, that means if it is here, if you go back, this sum equal to sum plus I, so essentially this particular expression is not depending on the x, right? That means I doesn't contain sum. So as a result, the calculation of this expression can proceed in parallel. Okay, that means all the threads will kind of keep evaluating what is this value of the expression, whereas only one thread is allowed to update it. Okay, so that is where the atomic directive can give better performance compared to the critical. Okay, of course that comes with a price, that your expression should not involve the variable. Okay, that means only the load and store of the variable x will be done in a mutually exclusive way using the atomic directive. Okay, so that's why atomic directive may provide better code or a faster code that basically has more optimization beyond what is provided by the critical directive. Okay, all right, so there are a couple of more miscellaneous functions followed by few more things in the work share constructs that we will kind of discuss in the next lecture. We're kind of out of time for today. Okay, I'm going to stop here. Talk to you in the next lecture. Okay, thank you.